right, so go ahead and get out your homework so I can swing by and check. Remember today we're checking 2 sheets. This was the first one from Friday. So go ahead and get out your homework. We're going to check that, and as soon as I'm done checking, we'll go over it.
Oh, I did that one.
Okay, guys. So I'm done checking homework. Let's go ahead and go over these. I did notice a lot of you skipped the ones where I gave you the endpoints of the diameter. Okay, but if y'all had walked through the door and I said, pop quiz, and I made it count, and I said, where is the center if you have the endpoints of the diameter? What could you have figured out? What do you think, Sarah?
I could have done it because you take the 2 endpoints and you do x1 plus x2 divided by 2, comma, y1 plus y2, divide that by 2, and then
Awesome.
there's your center, and then you plug that into the formula.
She nailed it.
I can't even see what you say.
She nailed it. That is exactly what you do. The center is the midpoint.
Could you just like count
Okay.
over and you plug it
If
in?
you had a graph,
No, I
you
wanted to
could.
find the radius.
If you did. Yeah. All
All
right. So,
plug it into the
this is
radius.
awesome that we can use problem-solving skills
That's the
to
center.
solve math.
When you plug in 2 coordinates.
All right. So, any questions about part 1?
Oh, yeah.
You solved one.
Wait, what now?
No, we can graph. Okay, part 2. Given an equation, can you find the center and the radius?
Yes.
Okay, now, normally I would never leave this as the square root of 18, but I'm not going to count off if you do. You should know this is equivalent to that. And if you don't, make sure you take the right kind of calculator with you when you go to take the SAT. Okay? So the square root of 24 simplifies to 2 roots
2
of
for
6.
x and 5 for y. And then you get r squared.
I will accept either on a test right now. Okay, number 3, write the equation. So you just need the center, you plug it in for h and k, and you square the radius. Plug in the center, square the radius. All right, this one, tangent to the y-axis. So where is negative 3, 2? Right here. If it is tangent to the y-axis, that means it's going to touch right here in one point, and the circle's going to look something, okay, more like a circle. All right, but the radius is that distance, and that distance is 3. So that's where we get the 9 from. All right, so sketch a picture, give it a try. Any questions about 4 or 5?
I got them all by myself.
Awesome. Yes.
On number 5, where did you get 49?
Okay, so this is the same problem. Well, very similar to the one before it. So let's redraw it so you can see it happen. All right, the point is 5, 7 this time. So it would be over here, down here, 5, negative 7. Okay, and it tells me this is the center, but this time it's tangent to the x-axis. So if I went directly up to where I hit the x-axis, that's where it's tangent. One little point right there. Okay, so what is the length of the radius? If this is down 7, the radius would be 7. So that's where the 49 comes from the radius squared. All right, let's take a look at the back. This is where we had to complete the square. So we took half the middle term, squared it. Half the middle term, squared it. But we have to add it to both sides of the equation. Now whatever you take half of ends up right here. Half of ends up right there. So take a look at problem 6 and see if you have any questions about parts A through D. Do you need to go to the bathroom or to the nurse? Okay. All right. Pick one and I will show it to you in real time. Which one do you want to see? 6B?
B.
The one with fractions? Sure. All right, so 6B. So our steps are this. 1, we group our x's, we group our y's, and we move the constant to the other side. So the 2 goes to the negative 2 goes to the other side and it becomes a positive 2. So now what we're going to do is we're going to create binomial squares so that it is in the form of, for standard form for a circle. So here we take half of positive 8, which is positive 4. We square that. So here we add 16. So here we do 2. Here we take half of positive 5, which is positive 5 halves. So when I square that, it's 25 over 4 because 5 squared is 25 and 2 squared is 4. So here I would add 25 fourths. So this becomes x plus 4 squared. So that trinomial factors to this binomial squared. This becomes y plus 5 halves. So this trinomial factors to this binomial squared. And that's the form we want it in so we can find our center, which is opposite, opposite. All right, so here we're going to add, this is 18, but this is over 4. So if I multiply by 4 over 4, I get 72 plus 25 is 97 fourths. All right, oh, no, I shouldn't say equals. So this is my equation right here. This line right here is the standard form for the equation of a circle. We've already found the center. Now we can find the radius. The baby's being a little iffy today. The radius is the square root of this. Well, I don't know the square root of 97, but I do know the square root of 4. So I'll leave 97 under the radical, and the square root of 4 is 2. So it's the square root of 97 over 2. And all of them work the same way. All right, so 7, you're given the center, you're given a point. So since you're given a center, you plug the center in, you plug the point in for your x and y, you solve for r squared. You plug it in. So we plug the center in, 3, 3. We plug in the point, so 1, 1. We simplify and get r squared is 8. So plug that in. All right, these. If you are given the endpoints of a diameter, you have to find the center and the radius. So to find the center, Sarah explained it so nicely earlier. She said add up those x's and divide by 2. Add up your y's, divide by 2. That is the center. It is the midpoint of that segment. So that's what we did first here. We found the center. And then we plugged in one of the points. And it doesn't matter which one you plugged in. We plugged in this one. We could have plugged in that one. You'll get the same radius. The radius isn't going to change depending on what point you pick. So we got r squared is 25. So what is the length of the radius if this equals 25? 5. Very good. So on this one, same thing. We had to find the center first. It's the midpoint. Plug it in. Okay, on the second worksheet, we're going to save for another day, a little closer to our quiz, and go over that one so that circles will stay fresh on our brains. All right, so today we're going to talk about the ellipse. This is not where I thought I was. So real quick, let me see if I can open up what I was looking for the ellipse. Okay, so what I have here is an infographic that was created for conics. And it first shows the 4 different types of conics: the circle, the ellipse, the parabola, and the hyperbola. And so it goes through and gives some, if we look at the St. Louis Arch, it's in the shape of a parabola. And we'll talk about parabolas and their strength when we get to parabolas. We have a Ferris wheel that is our circle. And then we have right here, we have something that we're going to go check out in a second. Some of you have already been there. It is the National Statuary Hall in Washington, D.C. It's at the Capitol. Have any of you ever been in there? There's lots of statues. Yeah? Okay, so there's something really cool about the ceilings in this hall. And we're going to watch a quick YouTube in a second to check that out. Because today we're talking about ellipse. And this is a good example of that. And then the last one we have is a hyperbola. And so here, what is this, guys? It's a cooling tower at a nuclear plant, right? Okay. And so there's a purpose for the shape of this tower. But the shape of the tower is a hyperbola. Okay? So we'll talk about that too when we get there. So really today is about the ellipse. And let's go back to this one. Yeah. Okay. So the ellipse. The definition of a circle was a set of all points in a plane that are equidistant from a given point, and that given point was the center. Well, an ellipse is similar, but what we do is we start with 2 points. And these 2 points are not the center, they're actually called foci. And so if I took a constant length right here, and so that this doesn't change, this plus this is going to be a constant no matter how I move it around. What it creates is an ellipse. And we tried to do this in one of my classes earlier today, and it kind of failed. So we're just kind of looking at it, this one, instead of actually trying to draw it on the board. But what it creates is an ellipse. An ellipse kind of looks like an oval, doesn't it? But there are a lot of special properties about an ellipse. Many of them reflective properties that actually are used in the real world. Really. Okay? So if we think about the parts of the ellipse, which we'll get to in a minute, we're going to look at it mathematically, but it does have some interesting purposes. And I want us to take a look at this quick video that kind of shares one of it.
President first, then served in the House, and thus far in our history, he's the only president who's ever done that.
He was
a wonderful speaker when he would give a speech down
Statuary Hall.
in his 17th year, he stood to give a speech one morning and he collapsed. He was carried off Lord to nearby hospital where he died 2 days later. His funeral was held elsewhere. But we've noticed something about the area. I'm going to go to the other side of the room and you can join me in a few moments. For now, I invite you to come in close and just lay your headphones around your neck.
Okay, so this sweet tour guide is a little older in age. Her voice isn't maybe as strong as mine. And she's leaving her group at this one spot in the hall. And she's about to walk across to the other end. Did you guys hear all the background noise of all the people in? All right. All take off their earphones so they couldn't hear her. She walks all the way across the hall, same voice, talking away from them, and they can hear her. Why? It is acoustics, but it's very special acoustics. It is math. It really is. They're standing at one of the foci. She walks to the other end of the hall and speaks at the other foci. Focus, if we're talking singular. And because of the reflective properties of the elliptical ceiling, what does her voice do? It bounces from one focus to the other. All right, so that's one of the properties of an ellipse. All of the conics that we're studying are used in architecture. Have you guys noticed that?
Yeah.
Things that are used in architecture. We're going to look at that closely a little later. But they have excellent properties. Did you guys pick up your notes on the way in?
Yes.
Yes? You all have them?
Yeah.
This is awesome. Okay, so the ellipse, the one we're studying today, is defined as the set of all points in a plane where the sum of the distances from two fixed points, and those are our foci, focus 1, focus 2, is constant. So if, let's say I said this length was 10, right here this might be 4 and this might be 6. Right here, from this point, if I measured from the focus to here, that might be 5. And from here to the other focus, that could be 5. Is it still 10? So no matter where I pick a point and I add the distance from this focus to the point and from the point to the focus, this might be 8 and this is 2. That distance is going to remain constant. The sum of those two. Yes, sir?
So are there foci on both axes or just on one?
The foci are always located on the longer axis. And that longer axis has a special name. The longer axis is called the major axis. The shorter axis is the minor axis. But you're right. The foci are always located on the major axis. All right. Now, this is the standard form for an ellipse. And we're going to work with this today. You'll notice it looks very similar to a circle. We have x minus h squared plus y minus k squared. That looks just like a circle. But what happens is they are divided by different amounts. So instead of being equal to an r squared, where they have the same coefficient, that would give us a circle. If these two were the same distance, it would be a circle. But since there are different distances, so let's look at it. Do you see the distance from here to here is longer than from here to here? So when we stretch it out one way or the other, if we took a circle and we stretched it, we're creating an ellipse, okay? So instead of having the same coefficients, these are going to have different coefficients. Now they're going to look like division. Like if this was over 4, wouldn't that be the same as 1/4? So what you're going to notice is that we have different coefficients. Looks just like a circle otherwise. They're both squared, it's a sum, but they're going to have different coefficients. That's how we know we're working with an ellipse. Now in the standard form, the ellipse is a sum. We've got that x minus h squared, the y minus k squared, but an ellipse always must equal 1. And so today we're introducing the ellipse. Tomorrow we're going to take some equations that aren't quite in the right form and get them into this form. Now with an ellipse we have a couple different things we're looking for to graph them. The first thing we're going to do is find the center. Just like we did with a circle. The center of an ellipse is HK. Now we define A as the distance from the center down the major axis to the end point. And I'll show you what that looks like in a second. So if we have this would be our A, the distance from the center to one of the endpoints of the major axis. So if we went all the way across, what would it be? Not just A, but 2A. So the major axis has a length of 2A. So this distance from the center to an endpoint is defined as A. The distance from the center down the minor axis to an endpoint is defined as B. So when we look at the formula, if we take the square root of this is going to tell us how to move from the center left and right. So I actually think of this as the horizontal distance. What's up under my X is that horizontal distance, left and right from the center. I think of this one as the vertical distance. So what's under the Y is the distance up and down from the center. Now C gives us the distance from the center to a focus. Now to find C is the square root of the bigger denominator minus the smaller denominator. So if we define A as the bigger one, it's A squared minus B squared. So if A is the bigger one, it's A squared minus B squared. The square root of A squared minus B squared. Whoops. I should have erased these. Alright, so there are two axes in an ellipse, the major axis and the minor axis. The major axis is always the longer axis, and you double A to get that length of the major axis. The minor axis is the shorter axis, and you double B to get the length of the minor axis. All right, a little more vocab. The endpoints of that major axis, so wherever your major one is, the longest one, the endpoints are called vertices. And we'll also notice on that long axis, the major axis, you will always find the foci. So the foci are always located on the major axis. Now, the endpoints of the minor axis are called the covertices. All right, so if this is our picture, we have some foci here. We have the vertices, which are the endpoints of the major axis. We have the covertices, which are the endpoints of the minor axis. And right here at the center is the center. All right, now this paragraph talks about something that's weird. It's called eccentricity. And eccentricity refers to the roundness of a conic. Okay? It's the ratio, mathematically we determine the eccentricity by the ratio of the focal length, that's C, to half the major axis, A. And the closer the eccentricity is to 1, the further the foci are for the center, and the more elongated, squashed looking your ellipse is. The closer it is to 0, the more it looks like a circle. So let's go see that in action. All right. So this talks about eccentricity. The eccentricity of a circle is exactly 0 because it doesn't deviate from a circle at all. A circle is a circle. So there's no difference between a circle and a circle. So it has an eccentricity of 0. Now, as the eccentricity gets larger, it turns into an ellipse. When it's exactly 1, we have a parabola, and when it's more than 1, we have a hyperbola. All right, so let's see if, here is the eccentricity. I'm going to get it, can't even see the circle, but it's there. Okay, as it grows, let's get it closer and closer to 1. Do you see how we get closer in 1? Our ellipse kind of flattens out. Do you see it flattening? Round. The closer the foci are together, the more it looks like a circle. The further apart, the more it looks like an ellipse. All right, so here we go. And let's see if I can stop it at 1. See how flat it's getting? We can't even see it. At 1, it becomes a parabola. I can't get it there exactly. And then if I keep going, you're going to see the other side of the hyperbola pop onto the screen in a second. Do you see it?
Wow.
Yeah, there's a hyperbola. Okay. Oh, I closed it. Man, that was a really good thing I was going to show you. It's gone.
No.
All right. Oh, well. Okay. This is about the foci also. So look how the foci are getting closer and closer and closer and closer, and doesn't it look more and more like a circle? All right. Now, when they are directly on top of each other, they're no longer a foci. It's now just the center of a circle. Do you see? Okay. And as they get further and further and further apart, we flatten it out. All right. So that's fun playing with an ellipse. And I closed down the one I wanted. I'll open that one back up tomorrow. We're doing ellipse again tomorrow. It's all good. Okay. So what are we looking at algebraically with this? Whoops. Didn't mean to do that. I'll just erase. Okay, we're going to go through step by step today. And today you're going to notice that all of our equations are already in the right form. So today they're already in a form for an ellipse. The x is squared, the y is squared. They have different numbers, different coefficients. It's a sum. The x is squared, the y is squared. They have different numbers. It's a sum. The x is squared, the y is squared. They have different coefficients. It's a sum. And in standard form, it must always equal 1. Okay? So all of these are already in the right form for us. And we just have to start learning how to pick off the right information. Now, the center of an ellipse you find the same way you did the center of a circle. So look at this equation. Is there anything added or subtracted to the x? Nope, it's 0. Anything added or subtracted to the y? Nope, it's 0. So this one has a center at 0, 0. Now, I can already tell from the equation that this one's going to be stretched horizontally. And the reason I can tell is, where's the bigger number? It's under my x. X represents that horizontal. So this one's going to be longer, elongated horizontally. Now, to find the distance that we move from the center, we take the square root of that denominator. The square root of 9 is 3. So I'm going to move right 3 to find a vertex and left 3 to find a vertex. Because this was the bigger number, these endpoints are my vertices. There's one at 3, 0, and there's one at negative 3, 0. I can add and subtract that 3 to the x at my center. All right, so if I went 3 this way and 3 that way, I can find the length of that major axis. I just double it. When I double 3, what do you get?
6.
6. Okay, now let's tackle our minor. So we look at that smaller one. We take the square root of 4. So we're moving 2. And this was under my y. So I move up 2 and I move down 2 from the center. So those co-vertices are at 0, 2 and 0, negative 2. So that minor axis has a length of what?
2. 4.
2 up and 2 down. Together makes 4. All right, now to the best of your ability, you will draw in an ellipse. My ability really stinks with the ellipse. Hopefully you're better than me. Alright, so now we're going to find those foci. We know they're somewhere on that major axis. They're somewhere on that major axis. So let's find them. So to calculate the focus, one focus, we would do a squared minus b squared. The bigger denominator minus the smaller denominator. And 9 minus 4 is just 5. So it is square root of 5 units away from the center. Square root of 5 left, square root of 5 right. So I've got to focus at negative square root of 5, 0. And one at positive square root of 5, 0. If you just want to write plus or minus root 5, 0, I'm good with that. All right, now to calculate eccentricity, it is C over A. We just found C to be the square root of 5. And A is 3. It's the square root of the larger denominator. So the square root of 9 is 3. So A is 3. So if we did root 5 divided by 3, that is approximately, and you don't have to do this, 0.75. It's kind of a flatter ellipse, closer to 1. All right. I'm going to go through number 2 real quick. The center is opposite, so it's going to be 1, 2. 1, 2. We're going to go right and left 2 units this time because 4 is under our x and the square root of 4 is 2. We're going to go up and down 4. So we go up 4, 1, 2, 3, 4. We go down 4. So this one's elongated vertically. There we go. The major axis this time is the vertical axis. It was 4 and 4, so it's 8. The minor axis is the horizontal. 2 and 2 is 4. My vertices were up and down 4. So it would be 2 plus 4, 6. 2 minus 4, negative 2. My coverts were left and right 2. So 1 minus 2 and 1 plus 2. To find the foci, I would do C, which is the square root of the bigger number minus the smaller number, root 12. If you wanted to simplify that to 2 roots of 3, you could. But this time, the foci has to lie on that major axis again, so I'm going to add and subtract that to my y. I would add and subtract that C to my y. And the eccentricity would be 2 roots of 3 over A is the bigger one, so it's 4. All right, that's how these work, and I'm going to have some helpers pass out the homework.
Oh.